Today we're talking about model comparisons in FlexPlot. So without further ado, let's get right to it. So remember, we have three reasons that we're going to do a GLM. One is to control for things, two is to study interaction effects, and three is to improve predictions, although in a video or two, I'm going to modify that list a little bit. But we're still stuck in stage 1 and 2, controlling for things and studying interaction effects. Remember that statistics really sucks at telling us whether a model fits well, but it's quite good at telling us which of two models fits better. And traditionally, to compare two models, what we did was we set up a null hypothesis, which basically says there ain't nothing going on. And then we compare that model to our model, which is kind of a straw man thing to do, isn't it? Really? You're gonna compare your model to nothing? Well, that ain't hard to win. That's like winning a baking contest against a slug. Ain't nobody impressed by that, y'all. But what we're doing with model comparisons is instead of setting up a null model, we're gonna set up a different sort of model. For our example, we are going to use a data set about depression, and we are predicting depression based on your mother's depression. And we will call that our null model, or our baseline model, or our reduced model. And we're going to compare that to a model that uses not only mother's depression, but also healthy eating and exercise. And the idea behind this is that mother's depression is a good surrogate for genetics, and we know that genetics plays a big role in depression. And so what we want to know is whether being healthy is going to reduce depression above and beyond your genetics. That right there is a model comparison question. So enough yakking, let's get into R, shall we? Welcome to my screen. I know that most of you are probably going to have the notepad on the left and the console on the right. There's a reason why I do that. Long story short, I started using R when I was a graduate student, and back then it was on Windows, and Windows defaults to having it on the right and having the console on the left. And so when I switched to Mac, I just kept it consistent. Anyway, it's just what I'm used to. So here's a bunch of code. You can see the link in the description to get your own set of code, as well as the data set. And this data set is simulated data. So we're going to start by requiring FlexPlot, and then we are going to go read in the data set. And I like to call data sets D. Why? Because I'm lazy, and writing D is much faster than writing depression. And so the first thing that we're going to do is we're going to visualize the reduced model. Again, that model says that depression is a function of mother's depression, which is kind of our proxy for genetics. And if we do that, we get this plot here on the left. And lo and behold, we find that the more depressed your mom was, the more depressed you are. Not surprisingly, and it is a nice, positive, linear relationship. Awesome! Well, not awesome to be depressed, but awesome that we have a model that fits. So now what we're going to do is we're going to start visualizing the full model as well. And so first I'm going to go first I'm going to look at exercise on the x-axis with eating and mother's depression in panels. And I'm going to add my ghost line so I can interpret what's going on here. And we get this plot, and I'm going to go ahead and make that bigger by clicking on this zoom button. And holy Hannah, that made it big. And so we got this ghost line that is representing average mother's depression and average eating. And what I'm looking for at this point is evidence of interactions. Now, hold on a minute. I realized I never explained my strategy, so here's what I'm doing. I'm first visualizing the full model and the reduced model to look for evidence of interactions. Because if there are no interactions, that simplifies our model immensely. So I'm trying to simplify our model before we start getting into the real model comparison stuff. Does that make sense? But also at the same time, we're comparing a full model which has interactions to a reduced model which doesn't have interactions. So it's all model comparisons anyway. Okay, and as I look at these lines, it looks like there's some deviations from parallel, like down here in this low depression, low eating plot. There may be a weaker relationship, but I don't think that's going to be big enough to mess up our model. So to me, this seems to suggest that there's possibly evidence of an interaction, but probably not. So I'm going to... How do I get out of that? There we go. Click the X, that's all you do. So that one plot showed that there is probably not strong evidence of an interaction. However, it is possible that we're getting kind of a biased view of it. Because here's the thing, anytime you do any sort of multivariate analysis like this, you're going to be compressing data. We took eating and mother's depression took it from a continuous variable that has lots and lots of unique values, and then we gave everybody one of 3 values in the visuals. And so that may be messing up our visuals. So it's very important to look at it from different perspectives. So what I'm gonna do is I'm going to put, instead of exercise on the x-axis, I'm gonna put mother's depression on the x-axis or healthy eating on the x-axis, just to, again, look for evidence of an interaction. So here is our second example there. And again, I'm gonna make this big. And what do we see? We see, for the most part, they are parallel except for this one right here, and I'm not at all worried about that one. Just because there are so few data points there, I don't trust that that slope has been very precisely estimated. So, I'm not too worried about that. And then I'm gonna go back to this one right here. And then again, I'm gonna zoom in on that. And what are we seeing? This one actually has 2 lines that kind of deviate significantly. So again, I'm kind of going back to the idea that maybe there's an interaction here. There's not strong evidence of an interaction. For the most part, all the lines look parallel, but just in case, let's go ahead and do some statistics. So to do that, we are now going to do a model comparison. And to do that in R, we're gonna fit 2 models. And this first model fits an interactions model, and this right here is shorthand. That star sign tells R to model the main effects and the interaction effects. And so what this is going to do is it's going to model the 2-way interaction between depression and exercise, exercise and eating, and depression and eating, as well as the 3-way interaction between the 3 of those. And we're going to have another model called interactions model that doesn't have any interactions. And so I'm going to run that one, and then I'm going to run that one. And then now I'm going to use the flexplot function model.comparisons, which is amazing because it's going to give us some statistics that are helpful for interpreting what's going on. Again, like I've said many times before, statistics are awesome, but they suck by themselves. And visuals are awesome, but they suck by themselves. We need them both together. So here we are, combining the 2. So again, our visuals said that maybe we could drop the interaction term. Now let's see if the statistics say likewise. All right, so I'm gonna move this over. For some reason, it doesn't put it all on one line when you do that. So I'm gonna run that again. And then what do we get? We get an R squared of the main effects model is 0.357. So we're explaining about 36% of the variance in the interaction model. That can't be
right. 3, 5, 6, 7. 3, 4, 7, 7.
That's weird. Okay, I just spent a few minutes double checking to make sure that there isn't an error in FlexPlot, and there isn't. And oddly, what we find is that the interactions model... Oh, did I just misname? I'm an idiot. Okay. Yay, math still works. So look what I did. I named the main effects model the interactions model, and the interactions model the main effects model. And so why this puzzled me was I was looking at the interactions model, and it said the R squared was 0.348, whereas the main effects model was 0.357. What? How can a model with more terms explain less of the variance? That doesn't make sense. And you're right, former Fife, who didn't realize his mistake, that doesn't make sense. Why? Because you misnamed the models, you moron. So look at that. Even a dude who has a PhD in quantitative psychology makes mistakes. Of course, that doesn't surprise any of you, does it? All right, now that we got our model situated, now we can look at the R squared. Again, I'm gonna pull that over. Now that makes sense. So we are explaining 36% of the variance with the interaction model and 35% with the main effects model. So we gain about 1% in R squared by adding those 4 additional terms. That ain't that impressive. So, according to the R squared, I'm inclined to say don't worry about it. Now the p-value, again, it is comparing the smaller model to the bigger model, and it's saying, and it's basically testing the hypothesis that adding those additional terms makes little difference. And the p-value suggests that there's really not a detectable difference according to the standard 0.05 thresholds, which are arbitrary, but whatever. But still, if the models are the same, this is basically saying that if the models are identical and those interactions truly add nothing, then observing an event like we observed, you'd have like a 40% chance of doing that, or 41% chance. So the R-squared says that interactions don't matter. The p-value says that the interactions don't matter. Let's look at the Bayes factor. So the Bayes factor right here, I just made a change yesterday and uploaded that on GitHub. So before that, it was kind of confusing what the Bayes factor was referring to. And so now what this tells you is it tells you how much evidence is in favor of whatever model is on that particular row relative to the other one. So this tells you that the evidence in favor of the main effects model is 11,189 times stronger than the model with the interactions. And of course, the inverse is true. The model in favor of the interactions model is 0 times stronger than the evidence in favor of the main effects model. So R-squared, p-value, and Bayes factor all agree that we don't need those interactions. And AIC and BIC, those metrics aren't very intuitive, and they totally depend on how many data points you have in your model and the type of model that you have, and lots of different factors that are just not consistent. So basically, what's the point? Both the AIC and the BIC give kind of a penalty for how many parameters you estimate. And so what you're looking for is you're looking for AIC or BIC values that are smaller. So the model with the smaller AIC and BIC is the model that we should favor. And here again, we favor the main effects model for both the BIC and the AIC. And this is awesome, this is helpful, this is unambiguous when this happens, that every single one of our statistics agrees that we ought to choose the main effects model. So I'm going with the main effects model. And we also have this predicted difference down here. Basically what that does is it takes the predictions from the interaction model and it takes the predictions from the main effects model and then estimates every individual score. And then it compares the difference between those two scores. So basically, if you have two models and one of them is much more complex, but they generate the same predictions, you don't need all that complexity. And so that's what these statistics tell you. So that tells you, and these give you the quantiles. So that tells you that the minimum difference between them is basically 0, so the two models are predicting identical things, and the maximum difference is 1.3 points. So we got a depression scale that goes from 0 to 20. The maximum difference between the two models that predict your score are only 1.3. So again, this seems to say that if the maximum difference is basically generating almost the same prediction, let's go with the main effects model. And that was all preliminary. That really didn't test our substantive hypothesis, but it was kind of necessary to make sure that the full model that we're comparing, which was intended to be a main effects model, is actually an okay model to compare to the reduced model. So now what we can do is we can go down to what is called the added.plot function. And so I've mentioned this before, and basically what it does is whatever term is entered last, it's going to put that on the x-axis, and on the y-axis it's going to put the outcome, except it's going to be residualized, or you're going to subtract out the effects of everything that comes before that. So for example, in this model right here, it's going to look at the effect of exercise on depression after controlling for mother's depression. And this one down here is going to look at the effect of eating on depression after controlling for both mother's depression and exercise. So let's go ahead and look at this first one. I'm not going to zoom just because it's pretty easy to see. So that tells you, again, the y-axis is depression after subtracting out the effect of mother's depression. And we see a negative slope, so the more exercise you get, the less depressed you are, even after you control for genetics or mother's depression or whatever. Awesome, so that gives some support to our hypothesis. Now let's look at eating, just for fun. And it looks like that too, maybe even a stronger slope than the exercise one, so that's good. Again, healthy eating seems to reduce depression regardless of one's genetics. Now what we could do is we can control for both depression and eating, and then look at the effects of exercise on that. And something kind of funny happens here is once you control for depression and eating, the exercise relationship basically goes away. That seems to suggest that exercise and eating are probably pretty correlated, and if you control for one, it kind of subtracts out the effect of the other, which isn't terribly surprising. And that's not harmful to our hypothesis either, because what we wanted to know is whether healthy eating and exercising are going to make a difference. And whether it's one or the other, we don't really care. So let's go ahead and look at the other one. So we're going to control for exercise this time and look at eating. And again, we have a negative slope, so there's still some signal left once you remove the effects of exercise. But in either case, again, it's cool, all's well. So far, what we've done with these added variable plots is great, it's awesome. But it's really not visualizing our hypothesis. Again, our hypothesis is let's control for mother's depression and look at exercise and eating. 2 variables. And these added variable plots have only really looked at 1 variable at a time, but controlling for the other things, it's still not visualizing those things together. And so that's where we're gonna get into compare.fits, but in order to do that first, we have to fit the model. So we're going to fit the full model, which has both exercise and eating, and we're going to fit the reduced model. And then now we're going to go down to compare.fits. And notice here, I'll move that over so you can see it all at the same time. Notice this comment. This will produce an error. What error, you ask? Why, by golly, fortunately, FlexPlot is very personable. It's your friend, it loves you, and it wants to give you as much information as it can. It says, sorry, I can't plot the model's lines when there are already lines in the plot. Try putting it in the given area. For example, y tilde x plus z given b should become y tilde x given b plus z. Or in other words, you can't have a plus on the left side of the vertical pipe. Makes sense? And the reason why is because when it fits the 2 models, it's going to show a line for the reduced and a line for the full. But when you add that plus in there, it's asking FlexPlot to show different lines for different values of eating or exercise or whatever. And so it makes sense. So let's go ahead and fix that. So we're going to go compare.fits depression tilde m underscore depression. This is just a FlexPlot formula, but now we're going to panel exercise and eating, and we're going to display the full and the reduced. So I'm going to click on zoom again so you get a full size page of this. Okay, so the full model is in red, and the reduced model is in greenish blue. And by the way, LM just tells you what type of model it is. That tells you that you fit a linear model. Okay, and so what we're looking for here is, it's not like what we did with interactions where we're looking for parallel or non-parallel lines. We don't care about that anymore. Although sometimes that's interesting. What we want to look for is, are the lines very different? Are they generating different predictions? And so I guess if in this area, if you happen to exercise none at all and eat moderately healthy, across the spectrum here, your predictions are going to be about the same. However, if you go up to here, we have pretty different predictions, and also we have pretty different predictions down here. This plot seems to say that those models are actually generating different predictions for the people. And of course, the full model is always going to fit better, but the question becomes, is it enough to justify it? For this plot, it's kind of ambiguous. I might be inclined to say, well, those predictions aren't all that different. Maybe we don't need those extra terms. But let's go ahead and look at it from different views. Again, anytime you do multivariate data, it's important to look at it multiple different ways. In fact, I have a note down here. It says, I prefer to put the extra variable on the x-axis. So right here we have mother's depression, which is the variable that we don't care about. Instead, I'm going to put exercise on the x-axis. And why is that? That's a very good question. The reason why is because whatever variable is on the x-axis, it becomes very easy to detect a slope. So it's very easy to see the difference between a flat slope and even a slightly positive slope. And so whatever variable is on the x-axis is going to become very, very apparent if it has a relationship with the outcome. But if you're paneling, it's not as easy to see that. So that's why I'm gonna, take turns looking at exercise versus eating, and something funny is gonna happen, but it's not actually a bad thing, it's actually a good thing. And so what happens is we see that with the reduced model, the line is flat, as it should be, because remember, the reduced model doesn't put exercise in the model, so it shouldn't care whether exercise is in the model. It's gonna generate the same predictions for everybody. And so now we see that, okay, maybe there is some evidence that we ought to keep these models. There's certainly some slopage. New slang term, I call it So this seems to say maybe we ought to keep the full model. All right, now let's look at it with a different view. This time we're putting eating on the x-axis. And again, I'm going to zoom. And now, holy moly, that became striking. And that's actually not all that surprising. You remember when we looked at that added variable plot and that exercise slope wasn't very steep, but the eating slope was a lot steeper. And so, not surprisingly, when we put eating on the x-axis, we see a much steeper slope. And so, based on this evidence, I'm inclined to, even look at this one, this plot right here. Anybody would look at that with any sort of training in statistics and look at that slope right there and say, no, that is a bad model right there. Now, of course, this isn't all that impressive either, but it's way better than the reduced model. And now, like we always do, we got the visuals, now we need the statistics to make sure we don't engage in confirmation bias, because of course we want this hypothesis to turn out to be in our favor, but we need to look at statistics as a little reality check. So we'll do model.comparison, and we got the same statistics as before, and look at that R-squared difference. So we used to be at 0.25, now we're at, or 0.26, now we're at 0.35, so almost a 10% gain in R-squared. That's impressive. And we got the p-value, which it's got e to the negative, so that tells you this is a number much smaller than 1. And so we got 9.58, or 9.5 with 9 zeros preceding that, so 0.00000, however many 9. So that p-value says these models are drastically different. And again, when the models are drastically different, you favor the full model, not the reduced model. And now if we look at the Bayes factor, that tells you that the evidence in favor of the full model is 460,000 times larger than the evidence in favor of the reduced model. And again, not surprisingly, the AIC and the BIC have smaller values in the full model than they do in the reduced model. And now we got our predicted difference. Minimum difference between them is 0, so sometimes the two models predict identical predictions between people. But on average, they are different by 3/4 of a point. So basically, the full model is going to be 3/4 of a point more accurate than the reduced model on this scale of 1 to 20. And the maximal difference is 2.5. So somebody's depression could have been over-predicted or under-predicted. This doesn't tell us, but it tells us we misestimated their depression by about 2.5 points. Boy, wasn't that fun? So that's a brief intro into doing model comparisons using FlexPlot and pairing visualizations with model estimates. I would highly recommend getting familiar with this sort of approach, this idea that we're visualizing things using added variable plots and doing model.comparisons and compare.fits, because we're going to use this strategy a lot in this class. So with that, we'll see you next time.